So good evening everyone. Welcome to the week 6 discussion of this course. Course Social Networks, and this course was taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Ropar. Myself, Ayan Paul. I am a PMRF Research Scholar from IIT Kharagpur, and I am a TA of this course. By TA, my duties are I will solve some of the question that will be very much similar to your assignment, so that whenever you are solving the assignment, it is not new for you. Okay, but before that, I always prefer to discuss what has been taught in this week, so that it will be easy for us whenever we are tackling the questions. Okay, so with this, let's start. So today's topic is about web graph. Last week we have discussed regarding this positive negative relationship and structural balance theory. Okay, now this week we will be talking about web graph. Okay, so what is the web graph? A web graph is a mathematical model of world wide web, www. Okay, so world wide web, everything that you are searching on the internet, it is related to world wide web. Okay, www. So where nodes or vertices represent the web pages, and direct edges, links, represent hyperlinks from one page to another. Okay, so here important thing is any social network can be modeled using nodes and edges. Okay, so two things are important: nodes and edges. So any social network, if you are given, you first have to understand what is a node in this social network, and what are the edges in the social network. So in a web graph or world wide web, the nodes or vertices, nodes are also known as vertices, edges are also known as links. Okay, so nodes or vertices, it represents web pages, and directed edges or links represent the hyperlink from one page to another. Okay, so that is regarding the web graph. Now one thing you have to notice, that it is a directed graph. Okay, so previously whatever friendship network or any network, so those graphs are undirected. Undirected means uh, undirected means there is no direction. Means if you are A is friend of B is also friend of A, but now it is a hyperlink. That means A page is related to B. That means there is a arrow from A to B. Okay, so if I will A and B, so there is a arrow from A to B. So B page is hyperlinked with A. That means whenever you will press a link on A page, you will be directed to B page, not the vice versa. It will not happen that whenever you will press a hyperlink with B, you will be going to it. That is not correct. Okay, so only one way, that is whenever you are on the page A, you can go to B, but not the vice versa. So this type of graph is known as directed graph. But whenever we talk about friendship like A and B, it is undirected graph. That means if A is friend of B, B is also friend of A. So that are undirected graph. So this is the difference between directed and undirected graph. So web graph or citations graph, these are examples of your directed graph. Okay, so this is how we can mathematically represent a directed graph GVE. Okay, G is a function of V and E. V is nothing but this vertices, and E is nothing but this edge. Okay, so V is the set of web pages, that is the vertices. Okay, and E is the set of hyperlink. Okay, that is the edges. If page A contain a hyperlink to B, we draw A to B like this. Okay, so this means users can navigate from page A to page B, not the vice versa, because it is a directed graph, so not vice versa. That means from B to A we cannot go, from A to B we can only go. So this is related to your web graph. Okay, so the main question in web graph is how to use it and how to get it. Okay, two questions. So first is how to get it, means how to collect the web graph. That is the first question. And second question is how to use the web graph. Okay, so in earlier whenever we have less number of pages, so we can say that we can hire some number of people who will be taking care of who will be collecting the web graph and taking care of the web graph, and also ranking the web graph. By ranking, I mean which page is superior to another, that they can discuss. Okay, if television technology, so if you hire 1,000 people with television technology, you just give the links of televisions. Okay, and keyword can be anything, and you have to give the article rating. Okay, so by that you are first collecting the link. So this part. Okay, how to get it, that means how to collect it. And this part, how to use it. That means if we rank those articles, we can say which article is superior to another. Okay, so by that we can use the web graph. Okay, so this is the thing. But now the problem is we don't have like 1,000 pages, we have million and billions of pages. Okay, so how to deal it? So for that we will be discussing about two ways. Okay, so first is collecting web graph by random walk method. Okay, random walk. Okay, so this is important. So what is this random walk method means? Random walk is a way to explore and collect the structure of a web graph by simulating how a user or random surfer navigates through the web pages. Okay, so again I am repeating, random walk method, this is the first method. Collecting web graph. So we are talking about collecting web graph. I have told you two important things are there. One is how to collect it and how to use it. So first is collecting. So how to collect it? So we do generally by random walk method. So random walk method is a way to explore and collect the structure of a web graph by simulating how a user or a random surfer navigates through the web pages. Okay, so random walk. You know what is random walk? You just start with your. Okay, someone is joining. Yeah. So you just use your vehicle and you just take random turns, and you can cover the entire city. Okay, so that is the random walk. Okay, so that policy we will follow in collecting the information of the web graph. So we will just start from a random page and we will be walking. Okay, so by that we can cover the entire web graph. Okay, so let's see what is the steps. Okay, so start from a web page, randomly follow the hyperlinks, record visited pages and links, gradually build the web graph. This simulates real user navigation behavior. So very important, very usual steps. So first is start from a web page. So you have to start from any web page, then randomly follow the hyperlink. Whatever hyperlink is there, you have to randomly follow it. Record visited pages and link, and gradually build the web graph. This simulates real user navigation behavior. So this is how you can collect the web graph. Okay, so this is collecting the web graph. Now step by step process. So let's see what is the step by step process for this random walk. So select an initial web page P0. Okay, P0 is our initial web page. Example, start from a news homepage. Then step 2, follow a random outgoing link. Okay, so from the current page, list all the outgoing hyperlinks, choose one randomly move to the link page. If page A links to BCD, randomly choose one. Okay, so this is the step 2. Step 3, every time you move, add a current page as a node if not already added. Okay, just add a current page as your node, because you have to collect the web graph, right? So web graph means you have to collect nodes, you have to collect edges. So at the current page, add a node, add the hyperlink to the direct page. Okay, so another node, you just take another node and just create a hyperlink. Okay, so if A hyperlink to B was followed, then add node A and B, add edge A to B. Okay, so step 4, repeat the process, continue walking for many steps. P0, P1, P0 is the initial page, then P1, P2, dot. Okay, so the longer the walk, the more complete the collecting graph becomes. So very easy. So first is choose a starting page, follow a random outgoing link, and record the edge. So these are the 3 steps, and fourth is repeat all the 3 steps. Repeat the process. So that is how step by step process to collect a web graph by random walk method. Okay, now there is a term known as handling dead ends, okay, or dangling pages. So if a page has no outgoing link, okay, for example, you are starting this P0 page, and this P0 page has no outgoing links or outgoing hyperlinks, then what to do? So in that case, there are two approaches: restart from a random page, jump to randomly chosen page. Okay, so you can just randomly jump to another page and see it, or use a damping, random jump probability. Okay, so you have to not just jump to a random page, but you can do it by some probability, with probability 1 minus d. Okay, jump to any random page in the dataset with probability D follow the hyperlink. Okay, so two things are there. One is probability 1 minus D and with one is probability D. Okay, probability 1 minus D, jump to any random page in the dataset, and with probability D follow a hyperlink. This ensures no getting stuck, better coverage of the graph. Okay, so this D is nothing but D is known as your damping factor. Okay, damping factor. So in PageRank random walk model, this D is known as damping factor. D is the probability of following a hyperlink. 1 minus D, probability of making a jump to any page. Okay, so with probability 1 minus D, we do the random jump. With probability D, we follow a outgoing link. Okay, so this is the theory. So typical value of D, in original PageRank model developed by Larry Page and Sergey Brin at the Stanford University, D equals to 0.85. That means 85% chance of following a link, 15% chance of jumping randomly. Okay, so this is how we have model whenever we have whenever we have to handle the dead ends or dangling pages. Okay, so this is regarding the random walk method, how to collect a web page. Okay, now second thing, most important node in a web page, that means how to use it. First is how to get it. This thing is how to get it. Now we will be seeing how to use the web graph. So most important node in a web graph is the point distribution method. Okay, to determine which node or which web page is most important, we use the uniform distribution method, also called as point distribution method, which is the foundation of the PageRank. Okay, so you can see who is most important. So what we do here, we just assign equal importance to all the page initially. For example, you are giving same amount of gold coins to each of the pages. Okay, so that is assign equal importance to all the pages initially. And then second, each page distributes to its importance equally among the page it's linked to. Okay, so each page, now what it will do, whatever pages it has been linked to, it will distribute its importance equally among all the pages. Repeat the redistribution process until its value stabilizes. The page with the highest steady state value is considered as the most important. Okay, so this is the idea of finding out the most important node in a web graph. Okay, so let's again see the processes or steps in this point distribution method. If there are n pages, then the rank of this pages initially, this is I. Okay, so initial rank will be 1 by n. Every node start with equal rank. Example, 5 pages, then each starts with the rank 1 by 5, that means 0.2. Then distribute points along outgoing links. So we have to distribute the points along the outgoing link. If page A has rank 0.2 and it has 2 outgoing links, then we will distribute this 0.2 rank with this 2 pages, with this 2 outgoing pages. So each link page now received 0.2 by 2 because we have 2 outgoing links, that is by 0.2 by 2. So now the pages will have the rank 0.1. Okay, step 3. For each page, you have to update the page rank with this formula. Okay, that is this. That means which is your page rank. Okay, page rank of J divided by out degree of J. Okay, so that is how. That means this process. Okay, so you have to just check what is the page rank of the previous page and how many outgoing links it will have. So by that we can get the page rank. Okay, so a page importance depends on number of incoming links, importance of linking pages, and how many links those pages distribute to. So these are the 3 important factors. First is number of incoming links. Okay, because number of incoming links will only decide the rank of that page. Okay, and importance of linking pages, and it will because we are uniformly distributed, then it will again important that how many nodes are connected to how many outgoing nodes are connected to this node. Okay, and how many links those page distribute to. Okay, so those are the three things. So these two are regarding the incoming and this is regarding the outgoing. Okay, number of incoming links and important of the linking pages. Okay, and then how many links those page distribute to. Okay, so this is the incoming I and this is the outgoing thing. Okay, O. So I and O. By that we can get the page importance or the importance of that web page. Okay. Step 4, repeat until convergence. After multiple iteration, value stabilizes, the system reaches a steady state distribution. The page with the highest steady state value is the most important node. Okay. The most important node is usually a page with many incoming links. Okay. Number of highly linked to highly ranked pages and linked by pages with few outgoing links. Okay. So what is important? This too is for the again incoming a page with many incoming links, because that is important. More incoming links, it will get benefit. Okay. And linked by highly ranked pages. Okay. That is important. The previous nodes with which it is linking, that should be highly linked, and linked by pages with few outgoing links. Okay. So these are the three things, because it receives a larger share if there is less outgoing links. So these are the three things that you have to remember remember in choosing the page, in deciding which page is the most important. Okay. And this is the thing. Now why this uniform distribution work? It starts with no bias. You can say this step, that we are assigning equal rank initially to all the pages. That means it starts with no bias. Importance emerge purely from the network structure. That means how many incoming links, how many outgoing links. It capture recursive influence. That means repeated influence we can understand. Then it models how authority flows through the hyperlinks. Okay. So that is why this uniform distribution works. Now this Google PageRank using web graph. So Google PageRank ranks web pages using this PageRank algorithm, which models the web as a directed graph. So Google is also nothing but a World Wide Web. So it ranks web pages based on this PageRank algorithm, which models the web as a directed graph. So same thing, because the World Wide Graph is a directed graph, so it models the web as a directed graph. The original idea was developed by these two gentlemen, Larry Page and Sergey Brin, at Stanford University, and later become the foundation of the Google search. Okay. So this is the PageRank idea. Okay. So this you just have understood. This is nothing but your PageRank formula, and this we give for this dangling nodes. Okay. This 1 by d by n plus d, that is we give this for dangling nodes, handling the dangling nodes. Dangling nodes means the nodes which does not have outgoing links. Okay. So to handle that, we give this formula 1 minus d by n plus d. Okay. So what is 1 minus d? Let me again get you there here. Yeah, 1 minus d is random jump. Okay. We will jump to a random page with 1 minus d, and with probability d we follow a outgoing link. Okay. So this is 1 minus d and d. Okay. So 1 minus d is 1 minus d is we jump to a random page. Okay. That is 1 minus d. So this portion is to jump to a random page, and this portion is when we are selecting a hyperlink. Okay. So these are two portions. First is this is random link, and this is random jumps, and this is selecting a web page. Okay. So these are two portion of this PageRank formula. Okay. So PRI, PageRank of I, that we are calculating here. N is the total number of pages. D is the damping factor, just we have discussed. And then we have this I and I, that is this pages linking to I. Okay. L and I, or this is I and I. So pages linking with I. And out degree J, number of outgoing links from J. This is out degree J. By this we can calculate the PageRank of the page. Okay. So how Google computes it? It initializes all page starts with rank 1 by n. Each page divides its rank equally among the outgoing links. Apply this damping factor, add the random jump term 1 minus d by n, this, and iterate, repeat until value stabilizes the convergence. Okay. So that is how Google computes the PageRank. Very simple. That same thing, uniform distribution method that we have discussed, same thing they apply to judge which is the most important page. So till now what we have discussed about web graph. What is a web graph? What are the nodes in the web graph? What are the edges in the web graph? Edges here is a special type of edges, not undirected edges but directed edges. Okay. And then what we have discussed, there are two important questions that we should ask from a web graph. First is how to collect the web graph and how to use it. So how to collect it? We generally go with the random walk method. Okay, so randomly we so let me show you. Randomly we choose a starting page and follow a random outgoing link and record the edges and repeat the process. So that is random walk process. Okay, so here one thing is important, that handling the dead end pages or the pages with no outgoing links. Okay, so how to handle that? For that we use a probability known as D, or damping factor. Okay, damping factor. So D is nothing but probability of following a hyperlink, 1 minus D probability of making a random jump to any pages. That is why the page rank has two things, 1 minus D divided by n, that is the first part, and plus D, the page rank formula, that is the second part. So 1 minus D is whenever we have to jump to a random page. Okay, that is 1 minus D by n, and D is probability of following a hyperlink. And then we have discussed about most important node in the graph, that we find out by point distribution method. Okay, so this is the point distribution method, that is assign equal importance to all the pages initially. Each page distributes importance equally among the pages it links to. Repeat the distribution process until value stabilizes and the page with the highest steady value. Okay, highest steady value is considered as the most important page. So how to use it? How to use it? For that we use the point distribution process to get the most important node in a, or most important web page in a web graph. Okay, so these are the steps. Okay, so by this we are getting the formula of PageRank by Google. Okay, so this is the formula of PageRank by Google. Again, I have told you we have this random jump section, 1 minus D by n, and we have this selecting a hyperlink D into this PageRank formula. Okay, PRJ means page rank of page rank, and out degree J means number of outgoing links from J. Okay, J is nothing but a node. Okay, so page rank of J divided by out degree of J. Okay, so that is how we calculate the page rank formula. Okay, this is total, we calculate the page rank formula. So let's discuss what is the difference between page rank and degree rank in web graph. Okay, so there are page rank we have just discussed. Now what is this degree rank? Degree rank measures the importance based on number of links. Very easy. So in web graph we have two degree, one is in degree and another is out degree. So in degree means number of incoming links, out degree number of outgoing links. So degree rank is the number of links. So that is degree rank, but that is not equal to page rank, right? Page rank, what is page rank? Page rank measures the importance recursively. A page is important if its important pages linked to it. Okay, so that is why this is page rank. Page rank is not degree rank. Degree rank is simple, number of links, the number of incoming links plus number of outgoing links. By that we can calculate the degree link, but that is not equal to page link. Okay, page link is a concept by Google. A page is important if important pages are linked to it. Okay, so characteristics here, if we say it is simple and fast to compute, definitely just addition. Okay, number of ingoing, number of outgoing links. Local measure look only at direct neighbors, does not consider quality of linking pages. Okay, because here we are not distributing any type of rank to the previous pages. That is why it does not consider the quality of linking pages. But here what we are doing, we are going with the uniform distribution method, so consider quality of incoming links. So that is very important. Global measure, here it is a local measure, because in a node like this, in a node you can only see what are the incoming links and what are the outgoing links. Okay, what are the outgoing links? These are the outgoing links. Okay, so incoming and outgoing, these are the incoming links and these are the outgoing links. That can only that it can only tell, that is incoming links and outgoing links. So this is a local measure. Okay, only local. Okay, so if this is your node, it is a local measure, but if it is a page rank, it is a global measure. Why it is a global measure? Now again you can say that this is linked with only its neighbor. Yeah, true, but what happens is the neighbors get the influence from previous neighbors also. That is why it is a global measure. Okay, use random walk with damping, converges to steady state probability. Okay, a page linked by 100 quality pages gets high rank. Okay, so this is the thing. Low quality pages gets high rank. So if we are going with degree rank, it will only consider how many links are there, but here it will consider what is the quality of the incoming links. Okay, so that is why this degree rank has limitation. That is why we move from degree rank to page rank. Okay, so this is the total theory of this week 6. So week 6, the web graph, collecting the web graph, equal coin distribution, random walk coin distribution, Google PageRank. Okay, implementing PageRank using point distribution and random walk method. Okay, so let's move to the question answer session. Okay, so here I will request everyone to participate in this session. Okay, so just I will show some question and try to answer it, and then we will discuss it. Okay, so with this, let's start the question answer session. Yeah, so social media, this is case 1, that is social media influence network, social media influence network. Okay, so a social media platform analyzes the influence of its top 5 users A, B, C, D, E through their follow relationship. A is the influencer, it follows B, that is content creator, and C, trend setter. B follows C and D, brand account. C follows D and E. D follows E. E follows A, creating a feedback loop. So again, what is the relation? A follows B and C. B follows C and D. C follows D and E. D follows E, and E again follows E. So this is the thing. Now, the theories that are required for this social media influence network: graph theory basics, node, you know what is a node, what is edge, directed graph, all these are directed graph. Okay, that means A follows B does not equal to B follows A. Okay, in degree, number of incoming link, out degree, number of outgoing link. This is the foundation of graph theory. Degree centrality, in degree centrality, it measures the popularity, how many follows you. Out degree in degree centrality measures the popularity, out degree centrality measures activity, how many follow you. Okay, so these are the two centrality. In degree centrality, it will measure your popularity. Out degree centrality, it will measure your activity. Okay, and then we have this page rank algorithm, we have discussed it. Okay, and then we have this random walk model, a random walk model also we have discussed this. We have this Markov chain. The distribution process is actually a Markov process with transition probability based on outgoing link, convergence to a steady state distribution. Okay, so let's start with the questions, so that will help us. What does each node represent in this network? A post, a user, a like, a comment. So guesses for this? Very easy. What does each node represent in this network? Guesses for this? Come on. What does each node represent in the network? Okay, no guesses. User, right? Each node represent a user. Okay, so in social media network, each node corresponds to users or account A, B, C, D, E. This has been given to the question. Post likes or comments are interactions, not entitled, not entities being connected. Okay, so this is the thing. Now option B is the correct answer, that is user. Now let's move on to the next question. What does an edge represent? A friendship, a follow relationship, a message, a shared post. Again, very simple question. Any guesses? Web graph is not a friendship network, so definitely it is not a friendship. It is a follow relationship. It is a message or share post, that we cannot say, but definitely we can say it is a follow relationship. That is A follows B. That is why we give A arrow to B. That means A is following B. Okay, so the edge represent nothing but a follow relationship. So option B is the correct answer over here. Okay. So a directed edge shows who follows whom. A directed to B, that means A follows B. Influence flows along this directed link. So option B is the correct answer. Let's move on to question number 3. If 10 influence points are initially given to each users equally and each user distribute their points equally to the users they follow, how many points does D receive after one round of distribution? Okay. Option A is 1. Option B, okay, let me just, yeah. Option B is 2. Option C 2.5 and option D 3. So any guesses for this? So let me just show you how to calculate it. So first, what has been given, there are 5 users. We know there are 5 users A, B, C, D, E, and they are given, according to the question, they are given 10 influence point initially. Okay, so each user will get 10 by 5, that is 2 points, because it is a uniform distribution method. That is why each user will get 2 points each. So 10 by 5 equals to 2. Each user split their points equally among users they follow. Okay, so follow structure relevant for D. B follows C and D. Okay, B splits 2 point, 1 point to D. Okay, so B will split 2 point because B initially has 2 point, right? And B follows 2 link, that is C as well as D. Okay, so B splits 2 points. One it will give to C and one it will give to D. That is why 1 point has been received. Okay, 2.5 is the correct answer. Yeah, 2.5 is the correct answer. But yeah, so let's explain how it is correct answer. B follows C and D. B splits 2 point, 1 point to D. Yeah, and C follows D and E. That means C splits 2 point, 1 point to D. However, C itself receives influence before distributing, which increases its effective contribution in page stylistic logic. So A to C it will give 1 point, B to C it will give 1 point. So C has 3 points. Okay, C has 3 points. C has 2 on its own, 2 from its own and 1 from A, but it redistributes based on the incoming flow. When C distributes, C sends half of its influence to D. Okay, C will send half of its influence to D. Okay, half of 3 is 1.5. So total influence D receive from B, it will receive 1 point. From C, it will receive 1.5. So total 1 plus 1.5, it will be 3. It will be 2.5. Okay, so 2.5 is the right answer. So again I am repeating. First we have to see this, that B follows C and D. Okay, as B follows C and D, and B is initially does not have any you can say B does not have any influence previously. That is why B initially has 2 points and it will distribute 1 point to C, 1 point to D. Okay, that means D will get 1 point from B. Okay, so this is very clear. Now what about now C also follows D and E. So D should get 1 point from C, as well as E should get 1 point from C. But what is happening here is C initially has 2 of its own and C is receiving 1 from B. Okay, so that is why C has 2 of its own, 2 plus 1 it is getting from B. So that is why 2 plus 1. 2 plus 1, and then C is distributing to D and E. So C will distribute 1.5 to D and 1.5 to E. Okay, so that is why D will get 1.5 from C. Okay, so D will get 1 point from B and D will get 1.5 from C. That is why total 1 plus 1.5, that will give 2.5 as the correct answer. Okay, so answer C is correct, 2.5. Okay, so any doubt in this? You can please ask. How we calculated it? Any doubt? No doubt, right? Okay. Nice. Now let's move on to the next question. Question number 4. Why use equal coin distribution in this network? To ensure fairness, to reflect user activity, to prioritize popular users, to simulate random events. So any guesses for this? Why we use equal coin distribution in this network? Very easy, to ensure the fairness. Okay. Equal distribution, it treats all users outgoing influence the same, avoids bias towards any specific follower, matches the basic assumption of page style model. Okay, so to ensure fairness, what we do, we use equal coin distribution in the network. So option A is the correct answer. Okay. Now let's move on to the question number 5th. Question number 5th, user C is followed both by A and B. User D is followed by B and C. Assuming all follow relationships are equal, who is more likely to have a higher page rank? D, B, C or A? Okay. So let's see how to do it. So page rank values both number and quality of incoming links. So C receives direct influence from A and B. A and B are early, well connected users. Okay, someone is joining. Yeah. So A and B are early well connected users in this network. Influence coming directly from strong or central nodes boost page rank more than influence passed along indirectly. Although D is followed by B and C, C's influence is partly derived, whereas C gets influence directly from two strong sources. This makes C page rank higher, especially in early or few iteration page rank calculation. Okay, so option C is the correct answer. That is C. Okay, option C, that is C, is the correct answer. So again, I am repeating, user C is followed by both A and B. Okay, user D is followed by B as well as C. So assuming all follow relationship are equal, who is more likely to have a higher page rank? So how we will explain this? C receives direct influence from A and B. A and B are early, well connected users in this network. Influence coming directly from strong or central nodes boosts the page rank more than influence passed along indirectly. Okay. Although D is again followed by B and C, C's influence is partly derived. We know C's influence is derived from A and B. So C gets influence directly from two strong sources. This makes C's page rank higher, especially in the early or few iteration of the page rank calculation. So C is the correct answer over here. Okay. Now let's move to the next question. Again, a numerical type of question. If 10 coins are randomly dropped on user, what is the expected number of coins per user? So any guesses for this? I hope everyone knows this. 10 coins are dropped on users. What is the expected number of coins per user? It is a uniform distribution problem. So answer will be 10 divided by 5 equals to 2. Okay. So option B is the correct answer over here. We have 10 coins and it is uniformly distributed among all the users. So 10 divided by 5 will give you 2. Okay. So 5 users, 10 coins dropped uniformly at random. So expected value 10 by 5 will give you 2. Okay. So each user on an average will receive 2 coins each. So option B is the correct answer. Okay. So with this we have ended the first case. Let's go to the second case, that is the case study 2, academic citation network. 4 groundbreaking papers in research field cite each others as follows. P1 2023 papers, it cites P2 2020 and P3 2021 paper. P2 cites P3. Okay. P3 cites P4 2008 foundational work. Okay. P4 cites P1, closing the citation loop. Okay. So again I am repeating, P1 it cites P2 and P3. P2 it cites P3. P3 cites P4 and P4 cites P1, closing the citation loop. So in this, what theory we should know? Directed graph, here node, it represents the entity, paper. Okay. Research paper. Okay. Paper. Our directed edge, it represents the citation, P1, P2, that means P1 cites P2. Okay. In degree, number of citation received. Out degree, number of citations made. Citation network are directed acyclic or cyclic graph. This is basic. Okay, someone is joining. Yeah, this is the basic graph theory for citation network. Okay, degree centrality, out degree centrality, it measures how widely a paper spreads its influence. A paper citing many others has high out degree. Students must understand out degree is not equal to importance. In degree often indicates popularity. Then PageRank algorithm, we know the PageRank algorithm we have discussed here, equal initialization, recursive definition, and influence propagation. Influence flow through the network iteratively. And then random walk we know with probability d, it follows a citation with 1 minus d, it jump to a random paper. This ensure convergence, no rank sinks, mathematical stability. Markov chain, page rank is Markov chain, transition probabilities are based on outgoing citation. The final page rank is a steady state probability distribution. Okay, now with this, let's solve the questions. What does a note represent? A researcher, a paper, a citation, a journal. So you all know what should be the correct answer. What does a note represent? A paper, right? A research paper. Okay, so option B is the correct answer. The note represent a research paper, a paper. Okay, in citation network, notes are academic papers, and directed edges represent citation from one paper to another. So option B is the correct answer. Now let's move to the next question. Which paper is most likely to spread its influence widely among through citations based on out degree? P1, P2, P3, or P4? So any guesses for this? Okay, so let's check how to do it. So out degree is number of citations a paper make. So P1, it has two out degree because it cites P2 as well as P3. Okay, so it has two out degree. P2 cites P3, only one out degree. P3 cites P4, so out degree is 1, and P4 cites P1. That means again out degree is 1. So P1 is the paper with most likely to spread its influence widely through citation based on out degree. So P1 will be cites most paper, and it spreads its influence widely. Okay, so P1 should be the correct answer. Option A should be the correct answer. Okay, so again I am telling you how to do it. P1 cites P2 as well as P3, so it has two out degree. P2 cites P3, it has one out degree. P3 cites P4, one out degree. P4 cites P1, again it has one out degree. So out degree of P1 will be more, so it spreads your influence most widely. Option A should be your correct answer. Okay, now let's move on to the next question. In the point distribution method, how points are initially distributed? Equally, by out degree, by in degree, randomly. So this you all know, right? In point distribution method, points are initially distributed equally. Okay, so option A is the correct answer. Okay, so very simple. In the point distribution method, the points are distributed equally. Okay, the point distribution method, PageRank style method, starts by assigning equal points to all nodes, ensuring a fair, unbiased initial state. Okay, so option A is the correct answer. Let's move on to the next question. Which paper likely has highest page rank? P1, P2, P3, P4. Okay, so outgoing rank, that is P1 is the highest, but what about page rank? That we have to calculate. Okay, now page rank rewards being cited by influential papers not having many direct citations. So P1, P3, P2, P3, P3, P4. So P3 receives influence from P1 and P2. P4 receives influence from P influence from P3. Okay, which itself highly cited and influential. Okay, so this means P4 accumulates both direct and indirect influence. So influence flows from P1, P2 to P3 to P4. So foundational paper often have high page rank despite low out degree. Even though P4 has only one direct citation, the citation comes from mostly influential nodes in the network. So P4 should be your correct answer. Okay. So again, I'm repeating, P3 it receives influence from P1 and P2. Okay. P4 receives influence from P3. So which itself highly cited and influential. Okay. So P3, if we compare P1, P3 is receiving from P1 and P2, and P4 is receiving from that P3. Okay, so P4 has the highest page rank. Okay, so this is how you can tell P4 has the highest page rank. So option D is the correct answer. So very simple. Just in this two sentences you can understand. P4 receives influence from P3, and P3 already has influence of P1 and P2. So that is why your correct answer is option D. Okay. So option D is the correct answer. Now let's move to the next question. In the random walk method, what does random jump probability 1 minus D represents? Start from a random paper, following a citation, ignoring citation, stopping the walk. So this also you know, in the random walk, what does the random jump probability 1 minus D represents? Starting from a random paper. Okay, that is the probability. 1 minus D is the probability of starting from a random paper. D is the probability of following the hyperlink. Okay, so 1 minus D probability of starting from a random paper. So option A is the correct answer over here. Okay. So in random walk method, we have this with probability D. Walker follows a citation. 1 minus D, the walker jumps through a random paper. Okay, this models behavior like discovering a paper via such recommendation or reading lists rather than following citation. Okay, so option A is the correct answer over here. Now let's move to case study 3, e-commerce product network. An online store tracks related product recommendation for 5 items. X laptop links to Y mouse and Z keyboard. Y links to Z and W, that is monitor. Yeah, mouse will link to keyboard and monitor. Yeah. Then Z links to W and V, that is headphones. That is keyboard links to W and V, headphone. Okay, W is the monitor and V is the headphone. W links to V. Okay, W is your monitor. Monitor will link to headphone. Okay, headphones link back to X, that is laptop, suggesting a bundle. Okay, so this is e-commerce product network. Now theories require directed graph. Nodes represent the products. Directed edges, it represents the recommendation links. Recommendation network is a directed graph. In degree, number of incoming recommendation. Out degree, number of outgoing recommendation. This is the basic graph representation of recommendation system. Okay. Degree centrality. In degree centrality, most recommended product. Difference between in degree, that is popularity, out degree, that is activities. Degree rank counts links only without weighting them. Okay. And then page rank, you know, if 10 points distributed and 2 point, each product will get 2 point, and then page rank is calculated recursively by this. Okay. And then expected value in probability, expected value total coins by total number of nodes. So expected value is nothing but this equal distribution. Okay. And then random walk interpretation, page rank models a random shopper clicking recommended product. Steady state probability, product visibility or popularity. Okay. So let's move on to the question. What does each node represent? A customer, a product, a purchase, or a review? So you all know it should be B, a product. Very nice. Okay, it should be B, a product. So in a product recommendation network, nodes are product, laptop, mouse, keyboards, and edges represent recommendation links between the product. So option B is the correct answer. Let's move on to this. When 10 popularity points are distributed equally among 5 products, which statement is most accurate? Each product receives 1 point regardless of its link. Product with more incoming links get more points. Each product starts with 2 points regardless of links. Products with fewer links get more points. So any guesses? Very easy. Each product will get 2 points each, because 10 points are there, and it is distributed among 5 products. So first what we do, we give each popularity points equally. Okay, so that is why 10 divided by 5, that will be equal to 2. So each product starts with 2 points regardless of its link. So option C is the correct answer over here. Okay, so option C is the correct answer. Now let's move on to the question number 14. If 10 coins are randomly dropped across 5 products, what does expected number of coins per product tell us? Each product is guaranteed 2 points. Some products may get all coins. On average, each product gets 2 points. Popular products always get more points. So again, very easy, same questions, but written in a different way. So yeah, 10 coins randomly drop 5 products. So on average, each product will get 2 points. So option C is the correct answer. Okay, random dropping does not guarantee equal outcomes for each product, but expected value. So this is the expected value because it is a random dropping and not uniform. So this is the expected value. So expected value will be 10 divided by 5 equal to 2. Okay. So option C is the correct answer. Now, why is PageRank better than DegreeRank for this network? Consider importance of linking product, faster to compute, user fewer resources, only consider outgoing link. Again, a very easy question. PageRank is better than DegreeRank because it considers importance of linking products. So option A is the correct answer. DegreeRank, it only counts how many links the product has. PageRank, it consider who is linking to whom. A product recommendation by important product, example laptop, to accessories, it gains more values. This better reflects a real purchasing influence. Option A is the correct answer. Now question number 16, which product has the highest degree rank? X, Y, Z or W? Okay. So any guesses for this? This is also very easy. Yeah. So option A, option C. So yeah, it should be option C. Okay. So see, Z, it has in degree link, X, Y and W. So 3 in degree link. W, it has 2 in degree link, Y and Z. V, it has 2 in degree link, Z and W. X, it has 1 in degree link, 1 V, and Y, it has 1 degree link, X. Okay. So since Z is recommended by most product, it has the highest degree rank. Okay. So highest degree, it has the highest degree rank. So option C is the correct answer over here. Okay. So degree rank in degree counts how many other products recommended a product. Okay. So that is why here we are going with only in degree link. So in degree link, Z has the highest in degree link. Okay. So option C is the correct answer. Now let's move to the next case, that is the case study for transportation network. A city's bus networks connects 4 stops: S1 downtown to S2 University, S3 mall. S2, S3 and S4. S4 is the airport. Now S3 to S4 and S4 to S1, completing the loop. Okay, so this is the transportation. S1 is the downtown, S2 is the university, S3 is the mall, and S4 is the airport. Okay, S1 is linked to S1. S1 is directed to S2 and S3. S2, that is university, is directed to mall and airport. S3, that is the mall, is directed to airport, and S4 to 1, that means from airport back to downtown. So this is the whole network. Now again, it is a directed graph representation. Note here represent the entities, bus stops. Directed edges, it represents the route between the stops. Transportation networks can be modeled as a directed graph. Concept of in degree, out degree, cycles. This it is a cycle, that is why Markov chain S4 to S1, it creates a loop. This is foundation graph theory. Equal distribution, so uniform distribution, basic average calculation, passengers per stop, that is total number, total passengers by number of stops. Okay. PageRank, this is the PageRank, this is the recursive formula, everything you know. This is random walk. Interpretation of PageRank is random walk. Steady state probability equals to long run fraction of time spent at node. In this case, probability of passenger is a stop is at a stop after many transition. Okay, so Markov chain, the network forms a Markov chain. Transition probability depends on outgoing link. The ranking is stationary steady state distribution. Okay, so let's go to question. What does each node represent? A bus, a bus stop, a passenger, a route. Very easy. It is a bus stop. Okay, so option B is the correct answer. Okay, bus stop. So in a transportation network, nodes are location stops S1, S2, S3 and S4. Edges represent connection routes between the stops. Okay. So option B is the correct answer. If 8 passengers are distributed equally, how many per stop? Again, very easy. 8 divided by 4. That will give you 2 options. So option B is the correct answer. 8 divided by 4 equal to 2. So option B is the correct answer. Again, very easy. Now, question number 19. What is the role of damping factor in the page rank for this network? It prevents infinite loops, accounts for random jumps, normalizes scores, handling the dangling nodes. So here, is there any dangling nodes? No, I don't think there is any dangling nodes here. So what it will do, it accounts for random jump, because we know that for with 1 minus d damping factor, it will do a random jump. Okay, so option B is the correct answer. Damping factor D, it models the probability a passenger or walker follows a route. 1 minus D represents a chance of random jump to any stop, preventing rank sinks and simulating spontaneous behavior. So option B is the correct answer. Okay. Now let's move on to the next question. S2 is linked by both S1 and S3. S4 is linked only by S3. If all links are equal, which bus stop is likely to have the highest page rank? Okay. So again I am repeating. S2 is linked by both S1 and S3. S4 is linked only by S3. If all links are equal, which bus stop is likely to have the highest page rank? S1, S2, S3 or S4? So any guesses for this? It will be S2. Okay, so S2, yeah, S2 has two incoming links from S1 and S3. Okay, S4 has one incoming link from S3. Therefore S2 accumulates more influence, giving it the highest page rank. So option B is the correct answer over here. Okay. uh, Question number 21. In the random walk method, what does the steady state probability represents? Likelihood of a passenger at a stop, number of buses at a stop, distances between stops, total passengers. So definitely total passenger is false, distance between the stop is false, number of buses at the stop is false, likelihood of a passenger at a stop is right. Okay, so yeah. So in random walk model, the steady state probability, long run fraction of a time a walker or passenger spends at each node. Okay. For a bus network, this translates to the likelihood of a passenger being at a particular stop. Okay, so that steady state probability means in this case. Okay, so option A is the correct answer. Now let's move on to case study 5. Online learning platforms, universities course prerequisites from a directed network. C1 intro to CS, directed to C2 algorithm, and C3 data structure. C2 to C4 AI. C3, that is data structure, to again AI, and C4 AI has no prerequisites. Okay, so this is the complete thing. Okay, so this is a course prerequisite from a directed network. So this C2 has a prerequisite of C1 and C3 also has a prerequisite of C1. Okay, C4 has a prerequisite of C2, that is the algorithm. So AI has a prerequisite of algorithm. C4 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 C3 is directed to C4. That means okay. So this is again I am repeating. So C1 intro to CS has prerequisite C2 and C3. Okay. C2 has prerequisite of C4, C3 has prerequisite of C4, and C4 does not have any prerequisite. Okay, so intro to CS has prerequisite of algorithm and data structure. C2, that is algorithm, has prerequisite of AI. The C3, that is data structure, again has prerequisite of AI, but C4 AI has no prerequisites. Okay, so this is the online learning platform. So it is again a directed graph. Node here, it represents the courses. Directed edges, it represents prerequisite relationship. The network is directed graph. Concept is in degree number of prerequisites, out degree number of courses depending on it. Hierarchical layered structure, this is foundational graph theory applied to the dependency network. Okay, so uniformly distribution, we know if 12 points are given, so 12 divided by 4, because 4 courses are there, so 3 per course. Okay, so again this is very we have discussed it again and again. Page rank, all these things we know. Dependency network and influence propagation, flow of influence through multiple layers, indirect influence C1 to C2 to C4. How recursive distribution, build ranking. Okay, Markov chain, page rank, models a random walk over course dependency. The final ranking is a steady state probability distribution. Okay, so what does each node represent? Very easy, option B, right? Each node represents a course. So option B is the correct answer. So in course prerequisite network, nodes are courses. C1, C2, C3, C4. Edges indicates the prerequisites. Okay. So option B is the correct answer in question number 22. Question number 23. If 12 enrollment points are distributed equally, how many per course? Again, very easy. That will be 12 divided by 4. That will be equal to 3. So option C is the correct answer. Points per course, 12 divided by 4 equals to 3. That is option C is the correct answer. Question number 24. Why use coin distribution for courses? Ensure equal popularity, simulate fair resource allocation, prioritize advanced courses, reflect student preferences. So again, very easy. Whenever you have this equal coin distribution, so it will simulate fair resource allocation. Okay, so it will start with a fair thing. Okay, so that is why option B is the correct answer over here. So yeah, simulate fair resource allocation, equal coin distribute, ensure each course start with the same baseline point. Okay, independent of its prerequisite or popularity. This models fair allocation before influence propagates through the network. So option B is the correct answer. Let's move on to the next question. C1 is a prerequisite for both C2 and C3. C4 is the final course. Which courses likely has the highest page rank? Whether it is C1, C2, C3 or C4. So C1 is the correct answer. Page rank flow backward from outgoing links, but notes that points to the many others. Like an entry, the course distribute influence widely. C1 is the entry point. It is referenced by no other courses, no incoming links, but it contributes influence to both C2 as well as C3. In the page rank term, C1 indirectly accumulates high rank because its importance propagates through multiple downstream paths. So C4, while receiving points from C2 and C3, it does not distribute influence further. Okay, that is why C4 has no prerequisite. Okay, so its sync nodes, sinks typically get damped unless the damping factor redistribute influence. So in prerequisite networks, starting course often have the highest page rank because they are essential for reaching all the subsequent courses. Okay, so option A is the correct answer over here. Okay, C1 is the is the course with the highest page rank. Option A is the correct answer over here. Now let's move on to the next question. In point distribution method, how does C4's rank depends on other courses? Only on its own links, on the page links of its prerequisites, on the total numbers of courses, not on other courses. So it will be as it is a prerequisite network, so C4's rank, page rank, will depend on the page rank of its prerequisites. Okay, so yeah, page rank of a course equals to sum of points passed from the courses pointing out to it. So C4 has no outgoing links. Its score comes entirely from C2 as well as C3. That is its prerequisite, which in turn depends on C1. Okay, so option B is the correct answer over here. Okay, so option B is the correct answer. Now let's move to the next question. Next case. Case study 6, news website network. 5 news sites linked to each other based on credibility. N1 global news, it is connected to, or it is directed to N2, that is Tech Daily, and N3 Eco Report. N2, that is Tech Daily, is directed to N3 Eco Report and N4 Health Watch. N3 is directed to Eco Report is directed to N4, that is Health Watch, and N5, that is Sports Network. N4 directed to N5, that means Health Watch is directed to Sports Network, and N5 is directed to N1. Okay, that is global news. So Sports Network is connected to global news, so it creates a cycle. Now here again, notes, it represents website or the news website network. Okay, directed edges, it represents the hyperlink web structure. It forms a directed graph concept in degree. Incoming links, that is credibility. Outgoing links, that is reference behavior. So cycle N5 to N1, it creates a complete loop. Dangling node, a dangling node is a node with no outgoing link. In PageRank, its points are redistributed equally to all nodes. Prevents loss of point total probability mass, ensures convergence. All these things you know. Random walk, you know. Here we have this 2 probability. D is the damping factor of following a link. 1 minus D, it is the jump randomly. Okay, and then quality versus quantity of link. Page rank is not equal to degree rank. A node can have low degree but high page rank. Importance depends on who links to you, the importance of linking nodes. Okay, it is recursive importance, that means repeated importance. Okay, Markov chain, page rank is Markov chain. Transition matrix represents link probability. Final ranks are stationary distribution. Okay, so just ignore this. Let's move to the questions. In the point distribution method, what happens to the points from dangling nodes? Lost distributed to all the pages equally, kept by nodes distributed to the linking pages. So any guesses for this important question? It is B. Okay, so it is distributed to all the pages equally. A dangling nodes is a page with no outgoing links. To prevent points from being lost, PageRank redistributes its score evenly to all the nodes in the network. This ensures the total points remains constant and the algorithm converges. So option B is the correct answer over here. This is an important question. Please note this. Okay, it is very important. Then in the random walk method, why include random jumps? Ensure all pages are reachable, speed up computation, prioritize important pages, handle cycles. So again it is important. So random walk method, we include random jumps to ensure all pages are reachable. Okay, so it ensures all pages are reachable. Random jump, probability of 1 minus D, allow the walker to jump to any pages even if not directly connected. This prevents rank sinks and ensure convergence, particularly in cycle or disconnected parts of the network. So option B is the correct. Option A is the correct answer. Question number 29. Can a website with low degree have high page rank? Yes, if linked by a high page rank site. No, page rank is proportional to degree only if it has outgoing links, only if it's a dangling node. So definitely it is yes if it's linked to high page rank site. So page rank, it depends more on the quality of incoming than quantity. A low degree site, few incoming links can have a high page rank. If few links come from influential or degree rank sites. Okay, or high rank sites. Okay, so option A is the correct answer over here. Last question. Why is PageRank preferred over DegreeRank for ranking websites? Consider importance of linking site, faster to compute, use less memory, handles dangling nodes better. Okay. So, okay, someone is joining. Yeah. So the answer is option. Why PageRank preferred over DegreeRank for ranking website? Consider importance of the linking site, because this is important. Okay, faster to compute? No, actually, this DegreeRank is DegreeRank is faster to compute than PageRank, so that is why this is false. Use less memory? No, it will use more memory than DegreeRank. Handles dangling nodes better. This we cannot say anything, but dangling nodes, if it is a dangling nodes, then again degree rank is more easy to compute, because it will have incoming link, it will not have outgoing link, so very easy to calculate the incoming links. So that is why this is also false. So option A is the correct answer. So degree rank counts only the number of incoming links. Okay. If it is a in degree rank, so here it has been in degree rank has been taken into account. PageRank weighs links by importance of the linking pages, capturing both quantity as well as quality of the links, which is essential for credibility based ranking. So that is why option A is the correct answer over here. Okay, so option A is the correct answer in this question. So with this, we have ended our question answer session. So we have the 6 cases. What about the cases that we discussed? So let me again go through. So this was the first case, that is social media influence network. Okay. So this is the first case, that is social media influence network. Okay. So this we have discussed. Then second case we have this. Second case we have this academic citation network. This also we have discussed. And third case. Third case we have e-commerce product network. Here also we have discussed. And then we have this fourth case, that is the transportation network. We have this fifth case, or the online learning platform, that is course prerequisite network. And at last we have this sixth case, that is the news website network. So 6 cases we have discussed. Common question, very each case, most common question is what are the nodes and what are the edges, that every case you should know. Okay. Second case, if you are given some amount of, for this and there, this methods question will occur for exam. This methods question will occur for exam. What do you mean? Can you please explain, Sneha?
Means this type of method will the occur of case studies in exam set.
Yeah, it can come. Definitely, it can come. Case study can be given, and
Okay, thank you, sir. Thank you for this.
okay. So yeah, so this are the things. Yeah, most common question is you should know first what is the node. Any case study has been given to you. First, you have to understand what type of graph it is, whether it is a directed graph or an undirected graph. If you have this friendship network, etc., these are undirected graph. Okay, that means A is friend with B, B is also friend with A. But here, this is this web graph. Web graph is a directed graph. That means A is directed to B. That means A follows B, but that does not implies B follows A. Okay. So this is the difference between directed and indirected graph that you should keep in mind always. Okay. Second thing, you should understand what is a node, what is a edge here. For example, if you have this e-commerce, let's take example of e-commerce product. So website. So e-commerce product of website. Here your nodes will be nothing but your products. Okay. And edges will be the connected or the connected products. Okay. So if I get A to B, that means like A is your laptop, and B can be anything like adapter or keyboard or mouse, etc. So A is linked to B. So This is the edge. That means when you will visit the A page, that is the laptop page, you will be redirected or you will be hyperlinked to this products like keyboard, mouse, etc. Okay, so that you have to understand what is the edge in each case. Third is this random walk method. Random walk method, it is very easy. Random walk method, only one thing you have to keep in mind: the dangling nodes. Okay, dangling nodes mean those nodes which does not have any outgoing links. So that is dangling nodes. To encounter dangling nodes, we have this concept damping factor D. Okay, so what we do if we have this dangling nodes or no outgoing link, what we do, we randomly jump to a different page with probability 1 minus D, or we follow the same link with probability D. So that is why two things, 1 minus D and D. Okay, so 1 minus D is important, so we randomly jump to any page with probability 1 minus D. So this also you have to keep in mind. Next thing is uniform distribution method. So uniform distribution method, you will be given some amount of coin or priority points or anything, you have to distribute equally among all the nodes. Okay, so this is another concept. And last concept is page rank. Page rank is not only the number of incoming links. So degree rank, if we just talk about in degree rank, so it is just the number of incoming link. But here it is not only number of incoming link in page rank, it is also quality of incoming link that is important. Okay, so these are the some of the concept that you have to keep in mind to solve all these questions. Okay, so with this, okay, so let me just show you some codes that will be okay, good. So let me stop sharing this. Yeah, so again we have this things. Yeah, we have this page rank using point distribution and page rank using the random walk method. Both will give you same result whether you go with random walk or the page distribution method. Okay, so I have given you the code like uh, similar thing. First, just you have to import the libraries and all. This is page rank using the point distribution method. Step by step, this is the page rank implementation tracking method. Just we have assigned 100 points to each node, and then we have history stores point at each iteration of the convergence plot. Step 3, keep distributing points until convergence. These are the steps. So step 1, create the graph. Okay, this is I guess step 4. This should be step 4. This should be step 4. Okay, and then execute, compare and scale, then all these things like visualize it, plot to compare. Yeah, so all these things. So let me just show you this curve. So this is a directed graph. Okay, so you can see this is a directed graph because arrows are there. Okay, so you can see this 4 is directed to 3, 2 is directed to 3, 1 is directed to 2, and 3 is directed to 1, as well as 1 is directed to 3. Okay, so this is the thing. So custom points, so we are distributing 100 points. Okay, 100 points to each of the nodes. Okay, and with this after 40 iteration, we get to know that first node is receiving 160 point, third node is also receiving 160 point. This is the first node, this is the third node. Okay, they both are receiving 160 point. Second node, that is receiving 80 points, and fourth node, that is receiving 0 point. Okay, so which is the most important node? First as well as third. Okay, and these are the plots you can see, first node. And yeah, so this is the custom point, and with custom point only we inbuild the rank, page rank will depend on your custom points only. Okay, so your page rank for this first node 0.4, 0.4, 0.2 and 0. Okay, so these are the ranks. Okay, so here you can see the convergence over time. So initially all the nodes start with the 100 point. Okay, so initially you can see all the lines, all the color lines. This is the blue color line, that is node 1, orange color line node 2, green color line node 3, and red color line node 4. So initially you can see all the nodes started with 100 points because we have given 100 points, assigned 100 points to each of the node. That is why initially it will start with 100 points. Okay, and then we are giving it 40 iteration, that is 40 runs. Okay, so after each iteration you can see how the points are changing. So this, let's take one line. Let's take the node 3. Okay, node 3, this is the line. So node 3, first it jumps to 250 and then it's coming back, and at last where does it ends? It ends around 160, that is 159 whatever. Okay, so node 3 is it ends at 160. Similarly, you can see this node 4, it just go to 0. Okay, after few iteration it goes to 0. And this another node, let's take the 2, node 2. Node 2 is this orange color. So orange color node, it start with 100 and then it is just after each iteration it has some value, and after few iteration it is converging to around 80. Okay, around 80. So this is how we are implementing the PageRank algorithm with point distribution method. Okay, similarly we can do the PageRank algorithm with random walk method also. It will give us the same result. Okay, same result, but here the ways are kind of different. Okay, it will give us the same result, but here the way is different. Okay, so we just you have can again see all this. Okay, again see all this. So this is the network this is the network graph. Okay, network graph size importance. So uh, uh, so uh, the size of the page will give us the importance. Like A is the most important, and then we have this B, then we have I think D, then B, then C, then E. Okay, so this is the random walk versus the in built, that will it will give you almost same thing. Okay, but here you just see that A is the most important node here. Okay, 0.35 something. Okay, and then we have this D, then we have this B, then C, then E. Okay, this is the convergence over time. Okay, so convergence over time. So all it is a random walk. Okay, random walk means it will not start with the same point. Okay, it will start with different scores. Okay, so after 40 iteration, or after, sorry, 30,000 iteration, this is the case. Okay, so after 30,000 iteration, your node A, or the blue color node, it achieves around, I don't know, around 0.33 something. Okay, and then this is the red color node. Red color node is the D, and it will get something value, and all these nodes it will get something value. But over the time, what will happen is each of the nodes stabilizes. Okay, this is the thing. And you can see here that total number of visits, or for the random walk also you can see it. Okay, so all these things, total number of visits, so all these things you can see. Okay, but this is important and this is important. So this is another thing that you can see. And we have this random walk simulation, that how many walks will it take to cover all the nodes. That is again an important code. How many walks does it, random walks does it require to cover all the nodes. Okay, so this is the thing. This is the thing. So I have to, it took, yeah, I have to, I think, yeah, I have to run the code. So just change the runtime. Yeah, let it be CPU. Okay, so just let me run the code. Okay, so this is the thing. Yeah, so this is the thing. Now we can run the simulation. This is number of edges, edge probability, and animation speed. Okay, so number of edges, let me increase to 34. Okay, and then run the simulation. See, it is running the simulation and it is covering node. Previously all the nodes are gray, but after random walk, what will happen is each node, if it is visiting any node, the color of gray node change to blue color. Okay, and the random walk is happening. So for 34 nodes, how many visit we require? So we are requiring 34 visit, and steps 87 steps. Okay, the steps are increasing, so visit will be 30. Okay, random yeah, sorry, this these are the nodes, and this is the visit. Visit means how many nodes it is covering, and this is the steps, that means how many steps that we have to take. Okay, so like for this 34 nodes, covering 34 nodes, 31 nodes, 32 nodes, it is 155. Okay, let us complete the simulation. 187, 190. Yeah, so in 212 steps it is covering all the nodes. Okay, so this is a simulation of random walk simulation. Okay, so again you can just play with this code, it will be interesting. So this is random walk simulation, and then we have this point page rank using this point distribution, and page rank with random walk simulation. Okay, so these are the three codes that I have given to you. You just open the code and copy here, that copy to the drive should be written, and you just copy this code to your drive, and then you can play with the code. Okay, no library you have to install, no library additionally, etc. If you are running the code in the local laptop or local computer, what you have to do is you have to first install all the libraries, and then you have to run the code. But if you are working with Google Colab, this is the advantage of the Google Colab. In this code only you can just import all the library, or install all the libraries, import all the libraries, and run the code at once. Okay, no need to install it to your local devices. Okay, so also by this there is no difficulty in if the libraries get updated, because what happens is Python, this libraries get updated with time. For example, the version something is like v1.1 is there, and after a few days v1.5 is there. Okay, so what will happen is you have to keep on updating your libraries, but here there is no things of that. Every time you run the code, every time you just install libraries and run the code. Okay, so that is why working in Colab is easy. So prefer working in Google Colab. So with this I am ending the session for today. Okay, we will meet on the March 10. Okay, March 3 I will not take the class. The March 3rd class is preponed to today, so March 10 I will be taking the class. Okay, so with this I am ending the session for today. We will meet on March 10, same time, 6 to 8 p.m.